Hey guys, it's Stephen Mossbrucker from the school group, back with another analysis failure here. So we talked about this in the end of the Micronics saga, which is this Nova model that this guy's working on, and he has a business called SLS4All. It's a pretty cool name, and this is a great video. We're going to watch it, and basically he's going to talk about his prototype. So that would be his phase three prototype to phase four, basically open alpha. He is basically doing open source, quote unquote, stuff. So we talked about the license in the last video, where his license basically says, hey, you can you can make as many of these as you want as long as it's not commercial, and you can use it and do whatever you want, right? So if we go here, we go down. So basically he talks about his implementation of going from a phase 3 prototype to a phase 4 alpha gate, right? So basically how he went from a prototype, and then how the prototype went, and then basically he finished his open alpha and then released it. And so he's basically talking about the gate from phase 4 alpha to phase 5 beta, right? So he's talking about here, okay, the open alpha is done. He didn't do a closed alpha because it's going to be open source. So maybe he did. I don't think he mentions it in this video whether or not he did the open alpha or not. But let's just say here, this is a closed alpha unit. So even in the thumbnail, it says, prototype versus full release unit. Okay, let's go ahead.
Hi guys! It took me quite a while, so I am really happy that I can finally introduce you the second evolution of my DIY SLS 3D printer.
So of course in here we're going to talk about safety, as well as design system Famica, as well as safety Famica bomb, and also the product hardware / product development guide here. So first off, we see a warning label. Unfortunately, it looks like the warning label is on the back of the printer. This area is on the back of the printer, and it looks like we have like a regular plug, right? We don't have any lockout system, it looks like this, to be able to lock this guy out. We would have to look at, okay, what's the segment this guy is targeting, and what are some of the other printers. Obviously in Micronics we didn't see that either, but I'm sure there can be a tiny little box, especially on the back, have a little lockout tagout set up for this, so you can lock it out if you're in a business to make sure that it doesn't get used, right? And then we got an Ethernet port here. But yeah, good to see warning label. Have some font with this. What class is it? What class of laser is it? Right? We talked about the radiation. Right here, radiation, right? Which class of laser is it? These are all this one, right? He's using IR laser, right? So characterized by frequency, wavelength, and energy. I think this is a 10-watt laser. Can do some serious damage, right? So specify that. Don't just have a laser logo. I mean, this is good. A lot of people probably wouldn't even have this. But what is the class, and what are the hazards? Here he talks about later, he's got a switch there that will not allow the laser to be shining without that guy there. Next thing you'll notice on the front, there's no EMO, emergency machine off, mushroom on the front. Just the on switch. So this is the inside. He's got some felt, and then here's the what he's going to talk about later, which is the lid present switch. So in case you In case you guys are not familiar, compared to the Micronics system, this is a classic two bin system. So you have like your so you saw the laser light is on the right side, and so he also has a galvo setup. So basically, on this side, it's filled with powder. This is a powder bin, and then this is the build chamber. And so it has a wiper, and it goes in a recoater or wiper. You can see it here on the left hand side, and this goes from left to right and moves a perfectly flat bed of powder over the right side and into the overfill bin is this slot right here, and that's that bin that he slid in the bottom.
I will show you what are the main design changes I have done between these two printers, and also will try to explain you what were the main reasons which led me to make them. It was nearly a year for me to move from the first prototype towards something I believe
1 year, right, guys? This is not a fast process, and especially if he's working just by himself. So same thing with Micronics, right? Why the acquisition kind of made sense for them. They're out of money. I mean, they would need the year, and they had a year for the Kickstarter, and he's not even shipping this. This is open source. He's going to do some kits as well as have DIY available, right? And this is what, $6,000 or so.
I can call the release candidate version, which means that once I will finish all my testings, I will open it to you and share the documentation.
His Fusion file is already released. I have it loaded in Fusion. We can show it later.
The main concept of the printer stayed the same. It means that you got the bottom part of the printer and the top part of the printer, which you can open, and actually to get direct
I think this was released 6 months ago.
access to the powder reservoir as
6
well
or
as
11 months.
print chamber.
11 months.
I chose this approach because I like that I have really enough space for taking out the powder cake once the print is finished.
If you look around, everything is inspiration. My best friends and I own Pirate Worldwide. We're on a mission to
First design change I'd like to point out relates to the powder reservoir and the print chamber shape. Although the overall dimensions of the both chambers stay the same like in the first prototype,
So you can see that there's definitely some things going on. It seems that the new version is bigger, similar screen, and then we have this one's got like a flatter setup. This one, well, it's got fans sticking out, but actually I think the fans are recessed. And this one has more of these chunky pieces here, and then obviously you see this one's like painted. This is all bare aluminum and things like that.
I had to make rounded corners inside them because of problems with the sealing. You can imagine that if you have really right tight corner, it's problematic to seal it somehow perfectly and to avoid the leakage of the powder.
So I believe, actually, I watched this video once already, and originally I thought that he's talking about leaking of the powder out of the corner, but now I realize what he's talking about is he's talking about leaking of the powder past the floor of the chamber. So there's a little plate that goes up and down, and when the plate goes up and down, it needs to not allow the powder to go past and get into other components and also leak onto your floor and collect on the bottom and, cause issues. So that's now what I believe he's actually referring to rather than sealing the powder inside the box. Because again, inside the box, you can just put tape on the outside and it won't come out, right? So this is true. Same thing in semiconductor. Generally, you don't want to have a seal going from a square corner because it's nearly impossible to seal with an O-ring and other forms, especially if you want a really tight seal. So it's always good to have very nice rounded corners. So again, this video is talking about kind of to see this iterative process of going from phase 3 to phase So going from phase 3 to going to phase 4 and releasing it and hitting phase 4 gate and getting the system out, right? So phase 3 is already done, was this one here that you can see on the left. And then this is basically his phase 4, and this is his kind of gate video, but not really, because he talks 11 months later where he released a video yesterday, or the day before yesterday, when Micronics was acquired.
Important to mention that powder leakage is problematic not just from the perspective of the mess and so on, but also that it can cause the layer shifting while printing. You can image it on the example of sand. If you'll put it on the box and then will you make a hole in this box, the sand will go out and it will cause the movements of everything what's in this sand. And that's
so he's talking about, like, if you have this powder cake, you can imagine if you drill a tiny little hole, the sand will, the powder will start to go through this hole, and thus the level will change. And the same thing as the sand clocks, right? So you have sand clocks. As the sand is going down through the center of that sand clock, in this middle has a hole that goes in, and the outside kind of stays at the same level but starts to fall in. So that's what he's talking about here, is that it's going to mess with your layers because this powder is leaking past the bottom floor of the chamber and into the rest of the tool.
actually the problem which can cause the layer shifting while printing.
So, it's named Famika. So it would be a component, chamber floor. So chamber 4 is possible failure modes, powder leaking past the seal of the chamber floor. Potential cause of failure modes, bad seal against the wall. Well, possible failure modes is like sand leaking, potential causes, powder leaking, potential causes of failure mode, bad seal from the floor sealing solution to the wall of the chamber wall. Effects of failure mode, there you go. You talked about it there. Layer shifting, mess, possible safety issue with humans and pets and other things. Other health concerns, could cause damage to other components, all these other things, right? What are your controls? So your controls are verify you have good seal. So severity obviously high because the printer is basically not usable. Occurrence is high because he's basically saying it happens every time. Detectability is high. The detectability is going to be high or easy, low. So it's going to be like 1. So this is like 10, 10, 1. It's like, okay, well, I can easily see it leaking into the bottom of the chamber, and I can kind of tell where it's coming from because it's going to have an outline of the chamber shape. So what is your mitigation plan? Change the chamber size to allow for more sealing solutions. Okay, severity doesn't have any more. Occurrence doesn't have any more. Detectability is still high. There you go. That's how you use the design system Famika.
When speaking about the chamber sealing, I had to change my approach completely. Not only with regard to the shape of the chamber, but also the sealing material and
So now he's talking about how he actually seals now with this new chamber design to ensure that he follows through on his change. So it's like, hey, I need to do a two-pronged approach, which is change the chamber wall shape and then upgrade my sealing solution.
sealing construction. In the first prototype, I used quite simple wiper sealing, which was made from the rubber silicone, which was silicone glued to the plate. The problem with the simple sealing approach was that when the bed went up and down, it behaved like a wiper, which means that the sealing did this and that. And that was the problem, because in the midpoint where the sealing was just changing its position, it made quite a huge pressure into the walls of the chamber, and build plate itself tend to move inside. And again, that relates to possible layer shifting, which we...
All right, so there's another big one. So now we'd go back to the design system Famika. Okay, number 2 is, all right, so you have your wiper solution. The one of the things is that it's moving up and down, and so it's moving the sand and it's moving the powder inside. That would be a dead fail for me, right there. Is that it's moving the powder around slightly when it's going up and down, and then basically what he's saying there is it's putting so much pressure on the wall. It's pushing out on the wall because the rubber doesn't really have anywhere to go because this kind of flap design is kind of primitive. It's the same thing that we use on windshield wipers, but the windshield wipers are spring loaded. It has somewhere to go. Here, it's trapped between a rock and hard place. It's clamped, it's glued to a piece of metal, and then shoved into another piece of metal. And so it's bowing out the side of the chamber wall, and when it's bowing out the side of the chamber wall, it's causing this plate to move and giving you some XY shift. So there you go. Seal. I would just put this also same thing, bed or chamber floor, build chamber floor. Possible failure modes is sealing causing print issues. Potential cause of failure mode is the seal is inadequate and it's getting stuck in the wall and bowing the wall out. Effects of failure, you have XY shift, XY layer shift, and also you could have Z not bonding issues because the flaps are pushing the powder around. Controls change your sealing setup.
Definitely didn't want to see there. Thanks to the people from my Discord server, I got an inspiration in EOS solution, which is using some kind of spring mechanism which pushes the sealing towards the walls of the chamber. And that's actually the approach I've chosen. So finally, there is not a silicone rubber for the sealing, but there is some kind of a technical felt which has really lower.
So here he's got basically springs here, and then he has this little foot, and these foot are pushing this felt into the corner so that you have good sealing, and also this is going to help center the build plate and not allow it to move. So also a big portion of this is you have to make sure that this build chamber with this type of mechanism, and even most mechanisms that you come up with, you got to make sure that build chamber is very in plane, right? Because if you have any sort of warps in the wall, and let's say you have a bump and it pushes on this spring, it's going to shove it the other way and then compress the other spring, and you're going to have an XY layer shift. So this is a challenging type of setup. You're going to want these guys to be as light of springs as possible to compress the felt here. Now, I'm not sure why exactly he can't just do a standard O-ring with a low durometer, something like high temperature silicone, and it should survive any of the temperatures he decides to throw at it, and relatively cheap, and should provide a good seal and good wear. But we'll see. I'm not sure if it's because of the wear factor, or maybe the metal's not that smooth, or maybe he's worried about skipping. But again, you can use a Teflon one, but that's a little hard. So I would just use like some sort of very low friction O-ring of some sort. I mean, I would have to look at it, but let's continue. But so far, pretty good solution here. Just use felt if that works well enough. So I think he's looking at the bottom side. So this is with the plate on, this is with the plate off. I think he's looking from the bottom of the chamber. So this is actually on the bottom side, and the powder's on the opposite side of this image. Pretty good
friction coefficient.
You see this is all machine components, right?
As compared to the silicone.
Another problem with the spring. Okay, how are you going to handle manufacturing with this? How are you going to handle make sure that these springs are all the same, right? Are you going to have some sort of professional spring manufacturer do it, and then are you going to do FAI, first article inspection, and make sure all these springs are very, very close with their spring Hooke's law coefficient, the K coefficient, so that they have the same spring tension. Also, how do you make sure they don't take a set and things like that with these, right?
So that's the solution which is in this version, and actually I'm really happy that it works pretty well. Next part of my design.
And again, with this, like we talked about in the Micronics marathons, okay, how long will this work? Can you have multiple of these machines? Keep using it. What does it look like when you've done 1,000 prints on multiple machines? In this case, he's doing kind of an open source / kit setup. So I mean, he's not going to have that many units out there in the field. Maybe he does, maybe he runs like 3 or 4 machines and then run them after he's ready to do this open release. Or in this case, he's just doing a little bit and then he's going to have other people build it, and then as it's quote unquote open source, and then create a update for his beta. Again, he's going basically into an alpha here. So yeah. But how long does this last? Do the springs taking a set have any effect, etc., etc.? These things need to be figured out before final version is agreed upon.
And I decided to change also relates to the precision of the movements in the Z1 and Z2 axis, which means the powder reservoir and the print chamber axis. In the first prototype, there were for linear guidance used common smooth rods of 8 mm in diameter, accompanied by linear bearings, and trapezoidal screw with nut to make the moves up and down. It's definitely not the bad way how to do it, but also not the best. If you will image that in the powder reservoir chamber is 8.5 something liters of the powder, if you fill it completely full, it weighs something. And from this perspective, I realized that the stiffness of this mechanism is not good enough. Therefore, I decided.
So basically what he's talking about is the physical weight of the powder could cause some bowing of those 8 mm rods, which are pretty common on 3D printers, and trapezoidal screws also pretty common on 3D printers. So that's kind of what he's talking about here, is upgrading it. Sure, it may work great on 3D printers, and you can see his solution right here on the other beta system. And again, here maybe should be protective cover, pinching hazards and moving object hazards, and any sort of labeling or anything. Right?
I decided to replace it with precise 12 mm linear guides accompanied by ball screw.
So here he just upped the kind of rigidity by going from linear rails, so shafts to linear rails. So they are constrained on the X, Y, and Z. X, Y, and Z. Well, in this case, let's say this is the Z. It's not constrained on the Z, but it's constrained X, Y, X, Y, X, Y, and X, Y. And then he upped the ball screw size to drastically increase the stiffness as well, and also the precision of any sort of up-down motion. Now with these are two separate systems. So this one is the build chamber. This one is the powder fill chamber. So they're not tied together, as you see.
It gave me the expected enhancements in rigidity of my approach, but it also gave me one big problem, and this is wobble.
To get started in data analytics, you don't need previous experience or a degree. The Google Data Analytics
I will not go in deep details of this problem because there are many videos on internet dealing with it, because it's quite commonly known from the FDM printers. But the main problem is that the ball screw is much stiffer than the trapezoidal one. So when it's rotating, it's making this kind of wobble, and you are unable to fix it in any clamp or something anyhow, because it's really, really stiff. And you can imagine that if this screw is wobbling like this, it will be transferred also into the build plate. And again, you have a problem with the print quality in terms of Z-axis surface and layer shift.
So this is kind of his battle he's going to have to fight with, is on that wiper assembly. How high of a spring force do you have? So if you have a very high spring force, it'll get rid of a lot of the Z-wobble. So the Z-wobble that he's talking about is as if the screw is not perfectly concentrically rotating, the ball screw, you can have this kind of shift left, right, on the X and the Y. And then as you're printing, you see a little oscillation of the Z-wobble. This is very, very common on SLA printers. You can Google SLA wobble. I actually have one of my small printers. I actually have it. I have that issue, and I have a part here on my desk that you can start to see the wobble. The further up it goes, it starts to get like a wobble, and then you start to see artifacts. So with the Z wobble there, you'll start to see pretty nasty printing artifacts, and you're gonna have to deal with that. So one, he can increase the spring force on the wipers to try to center it, but you're still on felt, so the felt's got some give. But if you do that, you're gonna see more amplification of any sort of warping on the build chamber wall or the fill chamber wall, right? But you'll see what he does here.
So I had another problem on the table I had to deal with. After some research, I decided to take pieces of inspiration from Wobble X approach, which I really like, but the problem is that it was designed for the FDM printers, and the Wobble X principle depends on gravity, which I can't depend here, because I need to be tight in both directions, up and down, because there is the main friction in between sealing of the print chamber and powder chamber. But finally I sorted it out. It looks like this, and it works pretty well. So if the printer is moving...
So basically he's got like some ball joints here. Originally looking at the 3D model, I thought they were rubber, but now they look like possibly steel. And so what I think he's doing here is that he's tightening this guy to try to get to try to level it. You can see a bolt going through here. And so these guys are kind of acting like pivot arms to try to level it. And then it's got basically these 2020 aluminum extrusion attached to the top. And it looks like this is printed. So this is printed, this is printed, this is printed. Yeah.
Moving with the beds up and down, you can see nearly nothing because
I am seeing a little bit out of
these movements of the balls are nearly microscopic. But what's more important for me is that the bed is quite nice and rigidly moving without any tendency for wobble.
And again, in the development process, there's a lot of instruments here that you can use. Dial indicator that has a logging feature. You can easily set up a dial indicator on that shaft and see if it's moving relative to the rest of the machine. But I did see, some wobbly here as it's going up.
You can see nearly nothing because these movements of the balls are nearly microscopic. But what's more is moving with the beds up and down. You can see nearly nothing because these movements of the balls are nearly microscopic. But what's more important for me is that the bed is quite nice and rigidly moving without any tendency for
again, what we're talking about here so is the movement of this plate left, right, forward, backward, because this is your fixture to hold everything together inside, and also the chamber wall as well. The chamber wall starts moving, you're gonna get some layer shifting on the XY plane as the print is progressing.
Nice and rigidly moving without any tendency for wobbling. If you like my project and don't want to miss anything, please subscribe here and also
probably going to be
some
sort of calibration set up there to get this XY.
Another area I had to place my focus on was the recoating mechanism. You can imagine how important is this assembly in the SLS printing, because the quality of each layer directly affects the quality of the whole print. Maybe you can remember from my previous video that I changed my approach from counter-rolling mechanism to the simple blade. The reason to change it is not because of wrong approach how to do it. It was just a little bit more complicated than the simple blade moving mechanism. In the first prototype, the
The
blade
later one, he has basically a roller that's rolling over the powder to flatten it out. While here, he just switched to a simple blade moving left to right to
was made out of
recoat.
3 mm thick aluminum, which was working quite well. The problem started in here. Even I used the same approach, I had quite a big problems with the vibrations of the blade, because the blade is connected to the belt just on the one side of the linear guys. So you can image if I started to pull the bell on one side, on other side, because this blade was not rigid enough, will start small vibrations. And of course
So he's pulling the blade on one side, and the other side, this blade has like some, it's running over the powder, so you have uneven loading, and also the friction in the linear rails here, or whatever. And basically what's happening is it's like a tuning fork, and it's vibrating as it's pulling over the powder, and the thing loads up, unloads, loads up, unloads, so it's causing even more oscillation. And so you're seeing this oscillation in the powder as because it's like it's moving back and forth, and maybe even some up and down Z, so it's probably causing some divots and some weird artifacts in the powder, which again, you want the surface as smooth as you can get it.
affected
And 3 millimeters is pretty small for those Eagle units, the Imperial units. It's about 1/8 of an inch, a little short. 3.125 is 3 point something is 1/8 of an inch.
the quality of the layer again. So I decided to make a blade thicker, which means that now is it from the, I think, 8 mm thick aluminum. I also changed a bit the bottom shape of the blade to have better quality of the surface of the recoated layer.
So basically, he went to 8 millimeter, which is 5/16 or so, from what I remember. And another thing that's interesting here, you would think, so here this looks like just maybe conventional milling or CNC milling. The gaps apart look pretty consistent. So the top and the bottom of this have to be very, very parallel to each other. So one, how does he have the parallelism from left rail to right rail? And also this guy is aluminum, and the top and bottom should be probably surface ground, and maybe you should go with steel, because how are you going to handle the expansion when you're heating the chamber and this guy starts to heat up, right? How are you going to handle the expansion, this guy bowing? So those are some of the things that he's going to have to think about to keep everything in tolerance when you heat up. Because remember, you always want to keep in mind your how your system is in its operating condition, as well as its starting condition. It has to be able to go from starting condition to working condition, but it has to, in operating condition, you want obviously the highest performance.
And it actually sorted.
And the reason why I'm talking about thermal expansion, aluminum has a very, very high thermal expansion coefficient, one of the
Out
highest.
My vibration problems, because the blade itself now acts also as a stiff gantry between the linear rails. Another problem I had with the recoating assembly was the belt itself. Yes.
And again, that's another thing that you can see with either high speed or with dial indicator attached to the gantry as it's moving, and going and looking at the end of this one, or even just put a because that guy has like a spring, on the indicator, so that could interfere with this a little bit. The other option is you can just put a accelerometer on there to look at the vibration.
It was temperature resistant, but it's not temperature stable, which means that under the higher temperatures, the belt will shorten quite a bit, and it make different tension of the belt. One it's cold and one it's hot. And it was quite a big issue because it overloaded the motor, and it was not good for the pulleys, for the belt, and for everything. In my first prototype, there were also like 3 or 4 pulleys used in the way of the belt, which I definitely wanted to avoid, because it's just make higher friction while belt is moving, and therefore I decided I want to have just the motor on one side and the pulley on the other side. And that's why I thought how to make this pulley not only the simple pulley, but also how to use it for tensioning the belt, and this is my solution. This approach makes me sure that the belt tension is
So it's a pretty standard 3D printing design of belt tensioning. So basically you have an overall bracket, and then you have basically a screw here to pull or push. It looks like in this configuration we're looking at a push. So you push it, and then it's not actually attached to here, so this guy's got a clearance hole, and then it's, or this guy should have a nut, but it depends on how he has it set up. And then he has a spring to make sure it doesn't go back and forth. Though with the spring, I'm thinking that it's not, it's actually a clearance, and it's pushing it off of this guy. But tensioning is going from left to right. So yeah, basically you pull this guy to tension it, and it's using these, you're using a bolt to kind of add spring, tension to the spring here. Or this is just a guide, but it looks like through here, it's a, through the light, it's a screw. Obviously we have the CAD model we can check. So a good idea to add, simplify, lower your part count, lower what can go wrong, how many mechanical components go wrong, and here add something that makes it very high performing and low temperature, and also keep the high performance at higher temperatures.
Make sure that the belt tension is equal under any condition. I mean, if it's cold or if it's hot.
If you make at least 150 grand a year and you're still embarrassed to take your shirt off at the pool,
If someone would ask me what I think is a really complicated thing on SLS printing, I would say for sure the temperature regulation. Especially the temperature regulation on the surface finish of each layer, which has to be heated up properly and evenly before the laser starts scanning. These temperatures should be somewhere in between plus minus 1 degree Celsius from the optimum, which is somewhere around 174-75 degrees Celsius for PA12. And it's not the easy task if you will image that you are regulating the temperature using these halogen bulbs. Here is the final solution of my release candidate version. And here you can see how it looked like in my first prototype.
And what's pretty cool is, you saw in the other video, he actually uses a IR sensor to power the halogens, is what it looks like. And you can see the IR sensor, not sensor, it's a camera. The IR camera on the screen is what he showed you. And he showed you a program of it breaking down the pixels to different segments, and then probably taking a rolling average of those segments and displaying it on the screen, and then calculating a dispersion to calculate how it drives these 4 zones. You'll see here, he'll talk about the zones in a second.
The main difference.
So you see here he's got, very specific zones here, no overlaps, right? So here he's got overlap. You can see one starts and one ends, and they go all the way from one end to another and overlap each other. Here it doesn't have, right? And so here also it does have some kind of division to help it not get other areas, and then also have a distinct area of light so you can control the sectors a little easier.
This is in the length of the halogen infrared tubes I used, because it was a problem to just buy in the shop the different lengths. Actually, you can buy 118 millimeters or 78 millimeters long bulbs. These are the 118. But if you will image that the print bed is 175 by 175, I had big problems with so-called cold corners, and therefore I had to add these 4 halogen bulbs into each corner. And it was the point where the printer was able to print something actually. Until that, it was just failing layer by layer. That's why I was really happy that I was able to find...
There you go, another mitigation, right? So design say to make a cold spot, halogen preheat. So halogen preheat, possible failure modes, not even enough, and you got some edge exclusion on the corners, or something like that, or it's just not heating in the center. Sometimes you'll have also the edge is tricky because it's touching the metal chamber wall. So you have the edge touching, and then maybe you have the center where you have all of these things overlapping. So the center's hot, edge is cold. So now you have like an edge exclusion, and then the top is melting, and now you have your print uniformity is really bad. So potential cause of failure, you have not adequate enough overlap. You need to control your overlap a little bit more, and also keep them from overlapping too much in the center. Effects of failure mode, what I just talked about. Or basically print failure or melting in the center, causing consumable waste, using more power than it needs to be, making the system uncontrollable, and overall not great at printing. What are your controls? Increase the length of the tubes and control the overlap of each zone to zone, and make sure that you go all the way to the corner and can control the corner. And then verify this with printing marathons and with your IR camera results.
Companies which were able to customize every parameter of this quartz infrared bulbs for me. It means the length, it means the wattage, it means the sockets, it means everything. It's really, really perfect.
So now he talks about, going to a manufacturer and getting a custom bulb. Okay, then you have, what is your agreements? How long are you going to have it for? When is it going to go obsolete? How are you going to control when it goes obsolete? What if there's nobody else that can make it, etc., etc., all these things, right? Yeah. Is there more than just this one player in the market that you can get a bulb from? And do you have agreement to support it for a certain amount of time? Things like that when you have these specialty design components.
So here I'm using
Especially
two lengths
OEMs.
of the bulbs, the shorter ones here and the longer ones here, so I can cross them without overheating them. And the outline of these bulbs is now equal to the total area of the print bed. Although I tried to think deeply about everything I was doing in regards to the design, there were also some underestimation from my side, like the behavior of the overpowder bin. You can see this is the overpowder bin from my first prototype, which looked like this. After I think 1 or 2 prints, it's completely deformated on this side because it's really hot in the chambers, of course. I came up with
I think this is because it's very hot, and also you're dumping 170 C plastic into it, plastic powder that's going through the overflow bin into this. So I think it's twofold there.
Couple of solutions how to make it better and how to protect this plastic part from the heat, but it will always finish like this. Yes, you can say why is it from plastic. It's just because I really want to keep this printer DIY as much as possible, and because of this shape of the overpowder bin, it wouldn't be easy to make it from the steel or from the aluminum sheet or whatsoever. So that's why. Therefore, I changed my approach completely, and now it's no overpowder bin on the side of the printer, just here underneath. Powder is going through the whole printer into this
That's also pretty good for mitigation, right? You can imagine you're walking behind the printer, you hit the overflow bin, it pops out and launches powder everywhere. Here it's underneath, right?
Powder bin, which you can just
was that little slot. So this is the build chamber, and then down 6 o'clock from this picture is the fill chamber. So as the wiper goes down inside this pocket here, it'll push anything else in this overflow bin. Another thing is, maybe we can do something about this this little ledge right here that'll cause plastic to get stuck here on this little ledge.
This overpowder bin, which you can just simply pull out like this and take it out completely if you wish to, and then just simply press it back like this, and to use this security knob to keep
also,
it in place.
Previous one didn't have a security knob, so this is also cool.
Yes.
and he's going to talk about the safety switches on the back.
Because I decided to open my plans to all of you after testing, I also had to start to think about my and your safety. So for these reasons, I added 2 safety switches in the...
Very smart guy, safety Famika, right? Talked a little bit about this, a couple videos of how to do the safety Famika. So your mitigation adds safety devices. So these safety switches are safety devices.
Printer. One is here in the top frame, and another one is here, protecting the over powder bin from removing it. This will directly switch off the laser when you will try to open the lid or pull out the over powder bin.
So again, protecting the user from the laser. Maybe have more of your documents. We could check out his documentation in our video. He does have documentation, but what does your more stickers for these dangers, as well as, and again, they don't have to be like, you can have stylized stickers, right? Follow OSHA and some of these things, whatever. Again, look at what is the industry standard, and then follow it or beat it. Follow it and beat it if you can. But you can even do stylized stickers. You can make it white with black font, and have white and black images, right? Just follow the same images, but you can change the color. Generally, they're white with black font. Sorry, yellow with black font, the images. But, you can mess with it. It's better than not having it. Having the laser warning, high temperature warning. I mean, there's 170 C inside that thing, so you'll just lift the lid up. And I saw in his design, he does have electromagnet to try to keep the lid closed. But how are these mitigations going to happen? And we'll have to see inside the manual. But good to have a lid present switch that when you open the lid, it shuts off the laser, shuts off obviously you also want to shut off the halogens and things like that. I think it just says shut off the laser, but you want to shut off the halogens. You don't want to be cooking somebody with 200 watts each halogens, right?
We have also made big changes on the electronics hardware and on the software side, but as these are quite huge topics, I decided to keep them for the separate video.
And I don't think he ever did release it. After this, he just released the product 2 days ago or something. So anyways.
So, that's it.
That's the video here, and yeah, this is his machine here. So I spent some time going through it and taking a look at it and seeing all of these, all the devices, and how it's kind of cool. Some of the ways that he sets these things up. Some of these things I'm not exactly sure. So he's talking about like these different holders and things like that. So I'm not exactly sure what some of these are, like maybe some sort of, the only thing I can think of here is it's like these are kind of like a strain relief cable strain. Oh yeah, that's what it is. Because you saw in the other picture, he had cables going down through here. So he had cable strain relief. So in this, that means that he doesn't have any cables modeled. So cable lengths and things like that are coming into question. Yeah, so here are cables. So yeah, another thing here, he's got pretty cool like open relays, solid state relays. Again, is there plastic here to prevent people from sticking their fingers in there, and the Ethernet, and also there is a fused power with the power switch, right? And then in the top here, so galvo window, I don't know if this might just be a little reflector that looks inside. Looks like a little reflector window. That was literally the whole thing. So it looks like it just looks directly in there and looks directly at the galvo. Okay, and then but yeah, you can see pretty interesting layout. I never seen this layout, nor have I done this way. About like he has all the screws in one kit, but I guess this makes sense because maybe this will match what he's shipping. He's got the belts in its own kit, so these would we would call kits. I can go into a video later talking about how this is laid out, but yeah, and I think I'm gonna do that. I'm gonna push it out to a different video. Yeah, so here you can see, kind of the setup and the shielding of the reflectors here. So basically these are reflectors. He's got aluminum high gloss reflectors that are polished. You can go here and look at, find in browser profiles here for the lid. Oh, there you go, top, okay. And then we can hide all the screws. And here's his covers, right? And we can go down here and pull off the bottom, take a look at that. Oh, this is a solid piece. So it seems like that's something that he can use to change the, go in and clean up the chamber body. So it looks like here he has another. Okay, there. So here's his spring assembly down here to have all his wipers. And then did he model? Okay, so it looks like he does not model the actual felt. But yeah, overall super cool. Maybe we'll go through and take a look at this model and get kind of my opinion further looking at this, and I'll look further through it, and we can also talk about that in a video. Okay, so that's it for this video. Go ahead and check out my school group, my exclusive school group on hardware development. I will see you guys in the next video. Take it easy. Peace.